In the beginning, when humanity first began to wonder about the nature of existence, the idea of what the universe was made of seemed almost beyond imagination. People saw mountains, rivers, fire, and air, and tried to find the hidden essence behind it all. Long before there were laboratories or microscopes, thinkers sought answers in philosophy and reason. Among them was the Greek philosopher Democritus, who imagined that everything was composed of indivisible particles he called tomos, meaning uncuttable. It was an extraordinary vision, a concept born not from evidence but from logic and intuition. Though he could not prove his idea, he laid the first stone on a path that would take humanity thousands of years to follow. For centuries, Democritus's atoms remained a philosophical dream, overshadowed by Aristotle's vision of a world made from 4 basic elements: earth, air, fire, and water. Aristotle's influence was so powerful that his view dominated science and philosophy for nearly 2 millennia. The idea of the atom, so small and elusive, faded into obscurity. It was too abstract, too mysterious, and lacked the means to be seen or tested. Humanity had to wait for both reason and experiment to unite before the true nature of matter could be revealed. The turning point came in the 17th and 18th centuries, as the scientific revolution swept across Europe. Thinkers like Galileo Galilei, Robert Boyle, and Isaac Newton began to challenge old traditions with the power of observation and mathematics. Boyle's experiments with gases hinted that matter might indeed be composed of tiny particles interacting in mechanical ways. Newton, too, speculated about the corpuscular nature of light, suggesting that even light itself might be made of small, indivisible particles. These early ideas breathed new life into the atom, not as philosophy, but as the foundation of a new kind of science. In the late 18th and early 19th centuries, chemistry became the key that unlocked the next stage of understanding. Scientists like Antoine Lavoisier and Joseph Proust began to uncover the rules governing chemical reactions. They observed that substances combined in fixed proportions, that elements maintain their identities even when forming compounds. It was as if nature was following a hidden mathematical script, precise, repeatable, and consistent. In 1808, the English schoolteacher and chemist John Dalton connected these clues into a single, elegant theory, the atomic theory of matter. Dalton proposed that all matter was made of small, indivisible atoms, that atoms of each element were identical in mass and properties, and that chemical reactions involved the rearrangement of these atoms into new combinations. His theory explained why water always contained hydrogen and oxygen in the same ratio, why gases behaved predictably, and why matter seemed to conserve its mass. For the first time, the atom was not just a philosophical symbol. It was a scientific reality. The atomic theory brought structure and meaning to chemistry and laid the groundwork for all that would come next. Yet Dalton's atoms were imagined as solid, indestructible spheres, like tiny billiard balls. They had mass but no inner life, no charge, no complexity. The mystery deepened as scientists began to push beyond chemistry and into the physics of electricity and light. By the mid-19th century, electricity was becoming one of science's greatest fascinations. Experiments with electrical currents in vacuum tubes hinted that there were particles smaller than atoms, entities that could move through space and carry charge. The world was on the verge of discovering that even the indivisible could be divided. It was in this age of wonder that Michael Faraday, one of the most gifted experimentalists in history, began to explore the invisible forces of electricity and magnetism. Faraday's work revealed that these forces were deeply connected, that electricity could produce magnetism and magnetism could generate electricity. Though Faraday did not deal directly with atoms, his experiments showed that matter and energy were woven together in ways that defied the mechanical simplicity of Dalton's spheres. The universe was not just a collection of particles, it was alive with invisible fields of force, pulsing and interacting in unseen harmony. As the 19th century marched forward, more scientists joined the quest to understand the hidden structure of matter. The discovery of cathode rays, mysterious streams of particles emitted from metal electrodes in vacuum tubes, became a turning point. In 1897, the British physicist J.J. Thomson identified these rays as tiny, negatively charged particles, far smaller than atoms. He had discovered the electron. The atom, once thought to be indivisible, was now revealed to have an inner world. Thomson proposed a new model to explain his findings, the plum pudding model. He imagined the atom as a sphere of positive charge sprinkled with electrons, like raisins embedded in pudding. It was a simple idea, but it raised profound questions. If the atom contained negative charges, where did the positive charge come from? And how were these opposite forces kept in balance? The old image of the atom as an indivisible sphere was gone forever, replaced by something dynamic and alive. Soon after, in 1911, Ernest Rutherford shattered even this model with his famous gold foil experiment. By bombarding thin gold foil with alpha particles, he expected them to pass through with little deflection, as the plum pudding model predicted. Instead, some particles bounced back, a stunning result that suggested atoms were mostly empty space, with their mass concentrated in a tiny, dense nucleus. The nucleus contained the atom's positive charge, while the electrons moved around it like planets around the sun. The atomic structure had been unveiled, but its mysteries had only deepened. This new planetary model of the atom fit the data, yet it raised an unsettling problem. According to classical physics, orbiting electrons should continuously radiate energy, lose momentum, and spiral into the nucleus, destroying the atom in a fraction of a second. But atoms were stable, the universe had existed for billions of years. Something was missing from the picture, something beyond the reach of classical laws. That missing element was quantum theory. At the dawn of the 20th century, Max Planck introduced the idea that energy was not continuous, but came in tiny, discrete packets called quanta. A few years later, Albert Einstein used this concept to explain the photoelectric effect, showing that light itself behaved like particles, photons. The boundary between particle and wave was beginning to blur. In this strange new world, energy and matter were no longer separate, they were two sides of the same reality. The atom, once imagined as a solid object, was now a storm of probabilities, forces, and transformations. Its mystery was not merely in its structure, but in its behavior. The electron, the nucleus, and the forces binding them could no longer be described by Newton's rules. They danced to the rhythm of quantum mechanics, a theory that would soon redefine the very meaning of existence. The evolution of atomic theory became not just a scientific journey, but a philosophical revolution. Each generation of scientists peeled away another layer of nature's disguise, only to find deeper complexity beneath. The atom was no longer the final answer, it was the beginning of new questions. What was inside the nucleus? What held it together? How could light behave both as a wave and a particle? And what role did chance play in the fabric of reality? From Democritus's invisible atom to Rutherford's nucleus and Bohr's quantized orbits, humanity's understanding of matter had undergone a transformation more dramatic than any myth or legend. The story of the atom had become the story of how humans see the world, a journey from imagination to mathematics, from faith to evidence, from simplicity to the profound beauty of uncertainty. As the atomic theory evolved, so did its impact on human thought. Chemistry, physics, and even biology began to merge into a unified picture of nature. The same atoms that made the stars were found in our bodies. The same forces that shaped the universe also governed the beating of a heart or the flicker of a neuron. The atom was no longer distant. It was the foundation of all life and matter, a link between the cosmos and the self. Yet despite centuries of discovery, the atom remained mysterious. Its parts were known, but their behavior defied intuition. Scientists spoke of probabilities rather than certainties, of energy fields rather than solid matter. The old boundaries between science and philosophy began to blur again. In trying to understand the atom, humanity had come full circle, back to the same awe that had driven Democritus to imagine the indivisible. As laboratories grew more advanced and experiments more precise, the atom revealed even greater wonders. Inside its nucleus lay protons and neutrons, themselves composed of smaller particles. Quarks, bound by the most powerful force known, the strong nuclear force. Around it, electrons moved not in orbits but in clouds, their positions governed by wave equations and uncertainty. The atom was no longer a simple unit of matter, but a vast and dynamic system, a microcosm of the universe itself. The evolution of atomic theory is one of humanity's greatest intellectual adventures. It reflects the courage to question, the persistence to explore, and the humility to accept that nature's truths are stranger than our imagination. Each step, from philosophy to physics, brought us closer to understanding not just what the atom is, but what it means to exist. This was the first great revelation that the visible world is built from the invisible, that matter and energy are intertwined in an intricate dance of probability and form. It is a story of curiosity stretching across millennia, guided by the light of reason and the spark of wonder. And as we look back on that journey, from the ancient philosophers to the quantum physicists, we realize that the atom's mystery is not something to be solved once and for all. It is something to be continuously explored, forever unfolding like the universe itself. Even today, the atom challenges our understanding. It defies simple definition. It is not a solid sphere, not a miniature solar system, not even a collection of parts in the ordinary sense. It is a symphony of forces, vibrations, and probabilities. Its electrons do not move along clear paths, but exist in a haze of potentiality. Its nucleus is not a static point, but a boiling sea of quantum energy, its particles constantly exchanging and transforming. The deeper we look, the more the boundaries between existence and possibility begin to fade. The atom, once thought to be the smallest piece of the universe, became a gateway to everything else, to chemistry, to light, to energy, and to the strange quantum rules that govern all of reality. The more we uncovered about it, the more we realized how limited our senses truly are. The world we see and touch is just the surface. Beneath it lies a universe of movement and uncertainty, where particles flicker in and out of existence, and where time and space themselves are fluid. Thus, the mystery and evolution of atomic theory is not just the story of science. It is the story of humanity's endless desire to understand. Every discovery built upon the imagination of those before. Every question led to deeper truth. And every truth, in turn, opened doors to new mysteries. The atom became more than a particle. It became a symbol of our own journey toward knowledge, the bridge between the tangible and the infinite. And so, as we stand in the age of quantum physics, looking back on the long path from Democritus to Planck, from Dalton to Rutherford, from Bohr to Heisenberg, we can see that the atom is not merely a unit of matter, but a mirror of our curiosity. It reflects the boundless nature of human thought, forever dividing, exploring, and redefining itself. The mystery remains, not because we have failed to solve it, but because the deeper we go, the more profound the questions become. The atom continues to whisper secrets of creation, energy, and the delicate balance of forces that hold the universe together. It invites us to look closer, to think deeper, and to never stop asking what lies within. As the 20th century advanced, the atom's mystery expanded rather than ended. What had begun as a philosophical idea had now become a precise mathematical language. Yet the closer scientists looked, the stranger the atom appeared. It was no longer a simple particle with predictable motion. It had become a realm of probabilities, a domain where intuition gave way to abstract equations and imagination had to stretch beyond all limits. Niels Bohr entered the scene with a model that bridged classical and quantum ideas. He imagined the electron not as a particle circling the nucleus freely, but as one that could occupy only specific orbits, fixed energy levels that allowed it to exist without collapsing into the nucleus. When an electron jumped from one orbit to another, it emitted or absorbed light of a particular frequency. The spectrum of hydrogen, once a puzzle of mysterious colored lines, now found its explanation. Bohr's model gave shape to the quantum idea and offered a glimpse into the invisible order hidden inside the atom. Yet even Bohr's atom was not the final word. It worked beautifully for hydrogen, but more complex atoms refused to obey its simplicity. In laboratories across Europe, experiments revealed inconsistencies, subtle deviations that hinted at something deeper. The electrons were not tiny planets after all. They behaved like waves, spreading out through space, interfering with themselves, and forming patterns of probability. Louis de Broglie, a French physicist, proposed a daring idea: if light could act as both wave and particle, perhaps matter could too. Electrons, he argued, possessed wavelength and frequency, just like light. His hypothesis was soon confirmed when experiments showed that beams of electrons created interference patterns, the unmistakable signature of waves. The boundaries between substance and energy dissolved further. The solid world had turned into a dance of vibrations. This revelation marked the true birth of quantum mechanics. Werner Heisenberg, working in a haze of mathematical symbols, stripped away the old image of particles moving along clear trajectories. Instead, he described electrons using relationships of observable quantities, energy levels, frequencies, and transitions, without imagining where the particles actually were. In doing so, he discovered the uncertainty principle, the realization that one could never know both the position and the momentum of a particle at the same time. The more precisely one was known, the more uncertain the other became. This principle did not simply describe a limitation of measurement, it rewrote the laws of reality. Nature itself was uncertain, its behavior governed not by strict cause and effect, but by probabilities. The deterministic universe of Newton gave way to a cosmos ruled by chance and possibility. The atom, once the symbol of solidity, became the emblem of uncertainty. Erwin Schrödinger, another giant of this revolution, found a way to describe this new reality through his famous wave equation. In Schrödinger's vision, the electron was not a particle in space, but a wave of probability spread around the nucleus. The atom became a vibrating field of potential outcomes, a cloud of mathematical possibility that only revealed its exact state when measured. This concept transformed the way we understood existence itself. The very act of observation influenced the outcome. Albert Einstein, though one of the fathers of quantum theory, resisted this idea. He could not accept a universe that relied on chance. God does not play dice, he famously said, arguing that hidden variables must exist to determine the behavior of particles. But decades of experiments confirmed the quantum view: uncertainty was not ignorance, it was truth. As quantum mechanics matured, the atom revealed its inner secrets with astonishing clarity. Spectroscopy exposed the intricate fingerprints of each element, showing how electrons occupied discrete energy levels. Quantum numbers described their spin, angular momentum, and orientation, a new atomic language that allowed scientists to predict the properties of matter with precision. Chemistry itself became an expression of quantum behavior: why water is liquid, why metals conduct electricity, why diamonds sparkle. All these phenomena were suddenly illuminated by the equations born from the atom's mystery. Yet every solved question gave rise to another. What was inside the nucleus? What held it together despite the intense repulsion of positively charged protons? The answer came from the discovery of the neutron in 1932 by James Chadwick. The nucleus was not just a cluster of protons, it also contained neutral particles that added mass and stability. But even then, the question of the forces that bound these particles remained open. The search for those forces led to one of the most profound discoveries of all: the strong nuclear force. Deeper inside the nucleus, physicists uncovered that protons and neutrons were themselves made of even smaller particles, quarks, bound together by gluons, the carriers of this powerful force. The simplicity of the old atomic model gave way to the complexity of the subatomic world. The atom, once imagined as the smallest thing in existence, now contained a universe of its own. By mid-century, Quantum theory had merged with relativity and electromagnetism to form quantum electrodynamics, a framework so precise that it could predict experimental results to more than a dozen decimal places. The atom had become a stage where the fundamental forces of nature performed their intricate play. Physicists no longer saw electrons orbiting like planets. Instead, they saw energy fields fluctuating in a vacuum, virtual particles appearing and disappearing in fractions of a second, and waves that could only be described by probabilities. Through these discoveries, the atom transformed from a physical object into a mathematical idea, an expression of relationships rather than things. Its mystery was no longer hidden by invisibility, but by abstraction. To understand it, one needed to enter the language of equations, where matter and energy were interchangeable, and where certainty was replaced by probability. This re-envisioning of the atom also transformed technology and civilization itself. The understanding of atomic structure led to the creation of semiconductors, lasers, magnetic resonance imaging, and nuclear energy. The same quantum principles that define the behavior of electrons inside atoms gave birth to computers, communication satellites, and modern medicine. The invisible atom, once a philosopher's dream, became the foundation of modern life. Yet in all this progress, the mystery never truly disappeared. As scientists probed deeper into the quantum world, they encountered paradoxes that defied common sense. Particles could exist in two places at once. They could become entangled, so that a change in one instantly affected another across vast distances, a phenomenon Einstein himself called spooky action at a distance. Reality, it seemed, was not local or absolute but interconnected in ways that defied the limits of space and time. These revelations carried the legacy of the atom's evolution into philosophy, art, and even spirituality. The atom had become a symbol of unity and mystery, showing that everything, from stars to human thought, was woven from the same quantum fabric. It reminded humanity that certainty is an illusion and that even the smallest fragments of matter hold infinite depth. The journey from Democritus to quantum theory also revealed something about the nature of knowledge itself. Each era believed it had reached the truth, only to discover that truth is not a destination, but a horizon that moves as we approach it. The atom teaches humility, that even with all our instruments and equations, we are still exploring shadows cast by a deeper reality. In modern physics, the search continues. Quantum field theory and the Standard Model describe the particles and forces that form the building blocks of matter, yet questions remain unanswered. Why do particles have the masses they do? What gives rise to the balance between matter and antimatter? What lies beyond the quantum fields, perhaps in the fabric of space, time itself? The atom's evolution has not ended, it has expanded into the cosmic and the microscopic alike. The development of particle accelerators allowed humanity to look inside the nucleus with unimaginable precision. Smashing atoms apart revealed a zoo of subatomic entities, mesons, leptons, quarks, bosons, each with its own role in the grand machinery of existence. The discovery of the Higgs boson in 2012 was another step in this unfolding saga, confirming how particles acquire mass. Even so, scientists know that the story is incomplete. Dark matter and dark energy, invisible forces that make up most of the universe, remain beyond the reach of atomic theory. This continuous search connects us to the ancient thinkers who first wondered what everything was made of. They did not have particle accelerators or quantum equations, but they shared the same longing to know the unseen. Across thousands of years, that same curiosity has endured, reshaping our understanding of nature again and again. The atom's story is, in truth, the story of human thought evolving from myth to measurement, from mystery to mastery, and from certainty back to wonder. Even as technology grows and theories become more complex, the poetic essence of the atom's mystery remains. Imagine that every breath you take contains atoms once breathed by ancient trees, by dinosaurs, by stars that lived and died billions of years ago. The carbon in your cells, the iron in your blood, the calcium in your bones. All were forged in the hearts of stars through nuclear fusion, then scattered across space when those stars exploded. The atoms that make you were born from cosmic fire. The atom is not just the foundation of matter, it is the storyteller of the universe, carrying within it the memory of creation. When we gaze into the night sky and see the faint light of distant galaxies, we are also witnessing the behavior of atoms billions of years ago. That light traveled across the universe as photons, quantum particles of energy, each one interacting with the world in ways that remind us how deeply the atomic and the cosmic are intertwined. The universe itself, vast and ancient, is a grand expression of atomic processes unfolding on an unimaginable scale. The mystery of the atom has shaped our sense of identity. Once, humans believed themselves separate from nature, observing it from the outside. But atomic theory revealed that we are composed of the same particles that form every planet, every star, and every drop of water. We are not apart from the universe, we are made of it. Each human thought, each flicker of consciousness, arises from electrical signals and atomic interactions within the brain. The quantum world made alive through biology. In this way, the evolution of atomic theory is also the evolution of self-understanding. It teaches that knowledge begins in curiosity and ends in connection. The atom's journey from invisible idea to scientific cornerstone reflects our own journey from ignorance to insight, from separation to unity. The more we understand the atom, the more we understand our place in the cosmos. Even now, as scientists explore quantum computing and quantum entanglement, the legacy of the atom continues to guide innovation. The strange laws that once seemed abstract now power the technologies of the future. Computers that calculate beyond classical limits, materials that defy ordinary physics, and communications that transcend distance. What began as a philosophical question, "What is the world made of?" has become the engine of modern civilization. Yet, in the quiet corners of scientific thought, a deeper realization persists. The more we know, the more we realize how much remains unknown. The atom's mystery is infinite because the universe it belongs to is infinite. Its story is not merely about breaking matter into smaller parts, but about confronting the boundaries of understanding itself. From the first spark of curiosity in ancient Greece to the blinding flashes of modern particle colliders, the evolution of atomic theory stands as a monument to human imagination. It shows that even in the smallest fragment of reality lies a reflection of the whole. That the universe can be found in a grain of dust and eternity in the spin of an electron. As the documentary of human discovery unfolds, the atom remains its central character, silent, invisible, yet ever speaking through the language of light, matter, and motion. It is a reminder that knowledge is not a destination but a journey, one that carries us from the visible world into the unseen depths where existence itself begins. And perhaps that is the greatest truth of all, that within every atom lies not only the essence of matter, but the echo of the human spirit. The same spirit that dares to question, to seek, and to wonder. The atom's mystery, like the universe it builds, is endless. It whispers to us that every answer is the beginning of a new question, and that the quest to understand what lies inside the atom is, ultimately, the quest to understand ourselves. In the late 19th century, the air of scientific discovery was electric, quite literally. Laboratories across Europe glowed with strange lights from glass tubes, where sparks danced through rarefied gases, leaving mysterious traces of energy. It was an era of fascination and curiosity, when the boundaries of physics were being pushed to their breaking point. The world had just begun to grasp the power of electricity, and yet no one fully understood what it was. Scientists could control it, measure it, even use it to power cities, but its essence, the secret of its flow, remained hidden. That secret would be revealed through a discovery so small, so fundamental, that it would forever change humanity's view of matter itself. For centuries, people had believed that the atom was the ultimate particle of matter, solid, indivisible, and eternal. It was thought to be the foundation of everything, a simple sphere that could not be broken down any further. The great chemist John Dalton had revived the atomic theory in the early 19th century, showing that elements were made of identical atoms and that chemical reactions were just rearrangements of these tiny, indestructible entities. His ideas had given chemistry a structure and precision it had never known before. But there was still one thing Dalton could not explain: how atoms interacted with electricity. Electricity had become a new frontier of physics. Scientists like Alessandro Volta, Michael Faraday, and James Clerk Maxwell had already laid its foundations. Faraday's experiments in the early 1800s had shown that electricity and magnetism were two sides of the same force. Maxwell later transformed that insight into elegant mathematical equations, revealing that light itself was an electromagnetic wave, a ripple in a sea of invisible energy. But these theories dealt with electricity on a grand scale. They described how currents flowed, how fields spread, and how waves moved, but they did not reveal what carried the charge. What was electricity made of? Did it move through atoms, or did it exist independently of them? To answer that question, scientists began experimenting with devices called cathode ray tubes, sealed glass tubes from which most of the air had been removed. When a high voltage was applied across two metal plates at either end, a strange greenish glow appeared on the glass wall. The light came from something moving inside the tube, something invisible that seemed to travel in straight lines from the negative electrode or cathode toward the positive electrode, the anode. These mysterious rays fascinated experimenters. They were called cathode rays, but no one knew what they really were. Some scientists believed they were waves in the ether, the invisible substance thought to fill all space and carry light. Others argued that they were actual particles of matter, tiny bits of the atom itself. The debate continued for years, fueled by conflicting evidence and by the limitations of the instruments available at the time. In 1897, at the Cavendish Laboratory in Cambridge, a quiet and meticulous physicist named Joseph John Thomson set out to uncover the truth. Using a refined cathode ray apparatus, he studied how these mysterious rays behaved under electric and magnetic fields. He noticed something extraordinary. The rays could be deflected, and the direction of deflection indicated that they carried a negative charge. This meant that the rays were not waves, but particles, charged pieces of matter. By measuring the amount of deflection and the strength of the fields, Thomson calculated the ratio of their charge to their mass. The result stunned the scientific world. The charge-to-mass ratio was far greater than that of any known ion or atom, about 1,800 times larger than that of the hydrogen ion, the lightest atom known. The only conclusion Thomson could draw was that these particles were much smaller than atoms. He had discovered something that lay within the atom, a new kind of particle, one that carried a negative charge. This was the birth of the electron. The word electron had been suggested earlier by the Irish physicist George Stoney, but it was Thomson's experiments that gave it substance. For the first time, the atom had been split, not yet in the nuclear sense, but conceptually. The indivisible atom was no longer indivisible. It contained structure, and within that structure, electric charge flowed in the form of electrons. The discovery of the electron marked the beginning of modern physics and ushered in a new era in which the very foundations of matter would be rewritten. Thomson's finding challenged everything that had been believed about atoms. If atoms contained smaller particles, what kept them stable? Why didn't the negative electrons simply escape or collapse inward? Thomson proposed a model to explain this puzzle. He imagined the atom as a sphere of positive charge with the electrons embedded within it, like raisins in a pudding. The positive charge balanced the negative charge, keeping the atom neutral overall. Though crude by later standards, this plum pudding model was revolutionary for its time. It showed that atoms were not solid and featureless, but dynamic systems with internal electrical balance. The discovery of the electron also bridged the worlds of physics and chemistry. Chemists had long puzzled over why atoms combined in certain ways and not others. The existence of electrons suggested that chemical bonds might arise from electrical forces, that atoms joined together because their charged particles interacted. Electricity was not just an external force, it was a fundamental aspect of matter itself. As news of Thomson's discovery spread, laboratories around the world raced to investigate these new subatomic particles. Experiments confirmed that electrons were identical, no matter which element they came from. Every atom, from hydrogen to uranium, contained the same tiny building blocks of negative charge. It was as if nature had used a single universal component to construct all matter. The electron became the first truly fundamental particle, the first glimpse into the subatomic world. Yet, in the wake of this discovery, new questions arose that no one could answer. If electrons carried negative charge, where did the positive charge reside? How were the two distributed inside the atom, and what prevented the opposing charges from simply neutralizing each other and collapsing into nothing? The atom, once so simple, had become a mystery again. The late 19th century was also a time of extraordinary change in physics. Old certainties were beginning to crumble. Experiments with light and heat radiation revealed inconsistencies that classical physics could not explain. The ether, once believed to fill all of space, was found to be unnecessary. Matter and energy seemed more connected than anyone had realized, and at the heart of all these puzzles stood the electron, the smallest piece of the universe ever known, yet somehow key to everything. J.J. Thomson's work did not end with the discovery itself. He and his students continued to explore how electrons behaved in gases, how they carried current, and how they interacted with light. Among those students was a young man named Ernest Rutherford, who would later revolutionize the understanding of atomic structure once again. But for the moment, the electron was the star of physics, the tiny particle that had unveiled the atom's hidden architecture. The implications of the discovery were vast. Electricity, magnetism, and matter were no longer separate domains of science. They were intimately connected. The flow of electrons explained how metals conducted electricity, how sparks leaped across gaps, and even how light could be emitted from hot gases. The mysteries of the universe were beginning to align into a single, unified picture. The discovery of the electron also marked the dawn of technology's atomic age. Vacuum tubes, which used controlled electron flow, became the basis of early electronics. From radio transmitters to the first computers, the understanding of electrons allowed scientists to manipulate matter in new ways, leading eventually to transistors, semiconductors, and the digital revolution of the 20th century. But beyond its practical impact, the electron forced humanity to reconsider what matter really was. For millennia, matter had been seen as continuous and solid, composed of smooth, unbroken substance. Now it was revealed as something granular, made of discrete particles bound by invisible forces. The solidity of the world was an illusion born from the vast emptiness between atomic parts. Even the simplest object, a stone, a leaf, a drop of water, was a universe of charged particles in motion. The classical understanding of the electron, however, was still incomplete. Scientists of the early 20th century treated it as a tiny, solid sphere, a point-like particle obeying Newton's laws of motion. They imagined electrons orbiting inside the atom like planets around the sun, held in place by electrical attraction. This mechanical vision seemed logical and even beautiful, but it could not explain certain observations. For instance, when atoms emitted light, they did so in discrete lines rather than a continuous spectrum. Why should electrons radiate specific amounts of energy instead of any value? Classical physics predicted that orbiting electrons should gradually lose energy, spiral inward, and collapse into the nucleus, yet atoms were stable. The equations of the old world no longer fit the new discoveries. The classical picture of the electron was breaking down. Still, in that transitional moment, the electron became the thread that connected the old and new sciences. It linked chemistry to electricity, light to matter, and theory to experiment. It was both a particle of nature and a symbol of change, the key that would unlock the quantum age to come. Thomson's experiments had opened the door, but no one yet knew how far that door would lead. In the years that followed, the electron would become the subject of countless investigations. It would reveal the structure of the atom, the secrets of radiation, and even the nature of light itself. It would inspire new theories and demolish old ones. From a faint green glow in a glass tube, humanity had glimpsed the machinery of the universe. The discovery of the electron was not just a scientific event, it was a turning point in how humans perceived reality. It marked the first step into the microscopic world, a world so small that it defied all direct observation, yet governed every visible thing. The electron became the bridge between matter and energy, between the tangible and the unseen. In its motion lay the forces that powered lightning, magnetism, and the very bonds that held atoms together. As the 19th century drew to a close, the stage was set for a revolution. The discovery of the electron had revealed that the atom was not the ultimate particle, but a complex structure filled with mystery. The classical world, with its clear boundaries, predictable laws, and mechanical precision, was beginning to dissolve. A new world was emerging, one governed not by certainty but by probability, not by substance but by energy. And at the heart of this transformation, the electron continued its silent dance, invisible, elusive, and endlessly fascinating. It was the smallest of discoveries, yet it carried within it the power to redefine everything humanity thought it knew about the universe. The new century arrived carrying the electric glow of possibility. The discovery of the electron had shaken the foundations of matter, but its meaning was still unfolding. Across Europe, laboratories buzzed with new instruments and new minds eager to probe the unseen world. The atom was no longer a philosophical curiosity, it had become a frontier. What held the electrons together? Where did the positive charge reside? And what invisible rules governed the motions inside that tiny universe? Among the first to seek answers was Ernest Rutherford, once Thomson's student, now a master of experimental brilliance. In 1899, he began to explore mysterious forms of radiation emitted by heavy elements like uranium. These emissions, soon labeled alpha, beta, and gamma rays, seemed to come from transformations within atoms themselves. The classical view of atoms as eternal and unchanging was beginning to crumble. If matter could emit energy spontaneously, then something profound was occurring inside its core. Rutherford's greatest insight came in 1909. In collaboration with Hans Geiger and Ernest Marston, they directed alpha particles, tiny, positively charged projectiles, at a thin sheet of gold foil. According to the plum pudding model, the alpha particles should have passed through almost unhindered, their paths barely disturbed by the diffuse positive charge within the atoms. But what the young researchers observed defied all expectation. While most of the particles passed straight through, a few were deflected at sharp angles, and some even bounced straight back. It was as though the alpha particles had struck something dense and massive at the heart of the atom. When Rutherford calculated the implications, he realized the atom must consist mostly of empty space, with nearly all its mass concentrated in a tiny central nucleus surrounded by orbiting electrons. It was almost as incredible, he later said, as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. The atom, once thought solid, was revealed as a miniature solar system, electrons whirling around a massive core. This nuclear model answered some questions but raised others. Classical physics predicted that the orbiting electrons should radiate electromagnetic energy continuously, lose speed, and spiral into the nucleus within a fraction of a second. Yet atoms did not collapse, they endured indefinitely. Why? The stable existence of matter itself demanded an answer that the old physics could not supply. The search for that answer led to one of the greatest leaps in scientific imagination. In 1900, Max Planck, studying the light emitted by heated objects, proposed that energy was not continuous but came in discrete packets or quanta. His idea was a desperate mathematical fix, never intended to rewrite physics. Yet it planted a seed that would grow into an entirely new conception of nature. A few years later, Albert Einstein took the next step. While analyzing the photoelectric effect, the way light can knock electrons from a metal surface, he proposed that light itself was made of quanta, later called photons. The electron responded not to a continuous wave but to individual energy bullets. This simple yet radical idea explained the experimental results perfectly and revealed a strange duality. Light could behave both as a wave and as a particle. The classical image of smooth continuity was beginning to dissolve. The electron, too, might not obey the mechanical laws that governed planets and pendulums. The stage was set for the emergence of quantum theory, where probability would replace certainty and where the invisible dance of electrons would be described by mathematics that defied ordinary intuition. In 1913, Niels Bohr, working in Rutherford's laboratory, crafted a model that combined the new quantum ideas with the nuclear atom. He proposed that electrons moved in specific orbits, each corresponding to a fixed energy level. An electron could jump from one orbit to another only by absorbing or emitting a quantum of energy, producing the discrete lines observed in atomic spectra. Bohr's model explained why atoms emitted light in precise colors and why they did not collapse. The idea was revolutionary, a blend of classical motion and quantum restriction. For the first time, scientists had a coherent picture of the atom, a tiny nucleus surrounded by electrons occupying quantized orbits. Bohr's theory brought order to chaos and matched experimental data with astonishing accuracy for hydrogen, the simplest atom. But beneath its success, unease lingered. The model still treated electrons as miniature planets circling the nucleus, a comforting but ultimately misleading analogy. When applied to more complex atoms, the mathematics failed. Nature was whispering that something deeper and stranger was at play. Meanwhile, the electron itself was becoming an experimental tool as much as a mystery. In 1919, the English physicist Charles Wilson perfected the cloud chamber, a device that made the invisible tracks of charged particles visible as delicate trails of condensation. For the first time, scientists could watch electrons and other particles carve their signatures through vapor, like comets streaking across a microscopic sky. The invisible world had become photographable. As researchers probed further, the boundaries between matter and energy grew blurred. Experiments with X-rays, radioactivity, and atomic collisions revealed a universe of transformations. Mass could turn into energy. Particles could appear and vanish. The simple solid atoms of the 19th century were gone forever. In 1923, the young French prince turned physicist Louis de Broglie asked a question that would transform physics yet again. If light can behave like a particle, could matter behave like a wave? He proposed that every particle, including the electron, had a wavelength associated with its momentum. Matter, he suggested, had a dual nature, both particle and wave. It was a bold hypothesis, but 2 years later, experiments by Clinton Davison and Lester Germer confirmed it. When electrons were scattered from a crystal surface, they produced diffraction patterns exactly like waves of light. The electron was no longer a tiny billiard ball. It was a wave of probability spread through space. This discovery shattered the last remnants of the classical world. The motion of electrons could no longer be described by Newton's equations. Instead, a new mathematical framework was needed, one that could capture the probabilistic, wave-like behavior of matter. In 1926, Erwin Schrödinger provided it. His wave equation described how the probability amplitude of an electron evolved in space and time. In this new vision, the atom was not a miniature solar system, but a cloud of possibilities, each electron existing as a diffuse wave around the nucleus, its position determined only when observed. Almost simultaneously, Werner Heisenberg developed an alternative approach known as matrix mechanics. His formulation dispensed with visual models entirely and focused only on observable quantities, energy levels, frequencies, and transition probabilities. From his abstract mathematics emerged the uncertainty principle, a profound statement about the limits of knowledge. One could never simultaneously know both the exact position and momentum of an electron. The more precisely one was measured, the more uncertain the other became. The classical world of absolute measurement had dissolved into a sea of probabilities. The electron, once imagined as a particle racing along a definite path, was now a quantum entity whose behavior could only be described statistically. Reality itself seemed to have become probabilistic, its certainties replaced by shimmering possibilities. The implications of this transformation reached far beyond physics. Philosophers wrestled with the idea that the universe was not deterministic but inherently uncertain. Technology, meanwhile, began to harness the new understanding of electrons. Quantum mechanics explained why materials conducted electricity, why some became insulators or semiconductors, and how light interacted with matter. Out of these insights came transistors, lasers, and the electronic revolution that would define the modern age. Yet amid this progress, the mystery of the electron deepened. What was it, truly? A particle, a wave, or something beyond either description? Experiments continued to reveal paradoxes. In the double-slit experiment, single electrons fired one by one through two narrow openings produced interference patterns, as though each electron had passed through both slits simultaneously. But when a detector was placed to observe which slit the electron actually went through, the interference vanished. Observation itself altered the outcome. The act of measuring changed reality. Such phenomena defied everyday reasoning. Yet they were confirmed again and again. The electron had become the ambassador of quantum strangeness, a messenger from a realm where logic bent and intuition failed. It reminded humanity that the universe was not built to satisfy human expectations. Even as quantum theory matured, physicists sought deeper understanding. Paul Dirac unified quantum mechanics with special relativity, predicting the existence of antimatter. Electrons mirror counterparts with opposite charge. His equations revealed a symmetry in nature and hinted at vast, unseen layers of reality. When the positron was discovered in 1932, the prediction was triumphantly confirmed. The electron had led the way not only to quantum mechanics, but also to an entirely new vision of matter and energy intertwined. Through the mid-20th century, the electron remained the cornerstone of both theory and technology. It powered radios, televisions, and early computers. Electron microscopes allowed scientists to see structures smaller than light's wavelength. Particle accelerators hurled electrons to near light speeds, revealing new particles and forces. The tiny charge discovered by Thomson now lit up cities, carried voices across oceans, and encoded the digital world. But as experimental power grew, the simplicity of the electron once again came under scrutiny. Was it truly fundamental, or could it be composed of something smaller? So far, every attempt to find substructure has failed. The electron remains point-like, with no measurable size, a perfect fundamental entity in the standard model of particle physics. Its properties, mass, charge, spin, are constants of nature, woven into the fabric of the cosmos. And yet, despite all the precision, the philosophical mystery endures. The electron is both everywhere and nowhere, both deterministic in its mathematics and uncertain in its measurement. It forms the currents in our nerves, the glow of our screens, and the bonds of every molecule in our bodies, yet it eludes direct comprehension. The more deeply scientists study it, the more it seems to blur the boundary between reality and abstraction. The story that began with a green glow in a glass tube has become the foundation of the digital civilization. The electron, once a curiosity of cathode rays, now defines communication, computation, and energy itself. It hums invisibly through circuits, encodes thought into binary pulses, and drives machines that extend human senses across space. In every instant, billions of electrons flow through the world's arteries of copper and silicon, their collective motion composing the heartbeat of modern life. But beyond technology, the electron's legacy is intellectual. It taught humanity humility, the recognition that reality is not what it appears to be. The solidity of matter, the continuity of motion, the predictability of cause and effect, all dissolve under the microscope of the quantum. What remains is a universe of patterns, probabilities, and elegant mathematics, a cosmos where the smallest entity connects to the largest truths. Every advance in science since Thomson's discovery has traced its lineage back to that moment when a faint glow revealed a deeper order. From quantum chemistry to nuclear physics, from superconductors to quantum computing, the electron remains the thread that ties the fabric of knowledge together. Even now, in laboratories probing quantum entanglement and the mysteries of information, the electron continues to surprise. It defies classical categories, embodying duality, uncertainty, and the paradox of existence itself. If one could imagine the universe speaking in its own voice, perhaps it would whisper through the motion of electrons, a language of energy and rhythm, of chance and connection. Each spark, each flicker of current, is a reminder of the invisible architecture underlying everything. The chair beneath us, the stars above, the neurons firing within our brains, all are dances of electrons bound by forces older than time. More than a century has passed since Thomson measured the deflection of cathode rays, yet his discovery remains one of the greatest moments in human understanding. It marked the transition from the visible to the invisible, from certainty to curiosity. It opened a door that has never closed, leading generation after generation deeper into the quantum labyrinth. The classical view that once defined science, a world of solid objects moving through absolute space, has been replaced by a universe of waves, fields, and probabilities. At the heart of that transformation lies the electron, the small traveler whose discovery electrified the modern world. It began as a spark in a vacuum, a flicker of light on glass. It became the foundation of all chemistry, the pulse of all technology, the clue to the structure of space itself. And though we can measure its mass to 12 decimal places and trap single electrons in magnetic fields, the wonder it evokes remains boundless. For the electron is not merely a particle of matter, it is a symbol of knowledge itself, tiny, elusive, endlessly in motion, forever leading us toward deeper truths about the universe we inhabit. At the turn of the 20th century, the world of physics seemed complete. The grand laws of Newton and Maxwell stood like towering monuments of certainty, describing both the motion of planets and the behavior of light. Scientists spoke with confidence of a universe that ran like a perfect clockwork, predictable, rational, and governed by mathematical precision. The atom, though still mysterious, was believed to obey the same mechanical principles that ruled the heavens. Every effect had a cause, every motion followed a law. The triumph of classical physics appeared absolute. And yet, in the quiet laboratories of Europe, strange cracks began to appear in this perfect order. Experiments began to produce results that defied all known theories. It started with light, that ancient mystery that had puzzled thinkers for centuries. For decades, physicists believed light was a wave traveling through an invisible medium called the ether. Its behavior, its colors, its reflections and refractions could all be described by Maxwell's elegant equations of electromagnetism. But there were questions those equations could not answer. Questions that grew louder as technology advanced. When scientists heated objects until they glowed, they noticed something strange about the light emitted. As temperature increased, the color of the light shifted, from red to yellow to white to blue. But not in the continuous way classical theory predicted. According to Maxwell and Newton, there should have been no limit to how much energy high-frequency light could carry. Yet the data disagreed. If the equations were right, hot objects should emit infinite energy at short wavelengths, a physical impossibility that came to be known as the ultraviolet catastrophe. In 1900, a German physicist named Max Planck approached the problem with desperate pragmatism. He was not trying to overthrow the old order, only to make sense of the data. But to match the experimental curve, he had to assume something completely new, that energy did not flow continuously, but in discrete packets he called quanta. Each packet's energy was proportional to its frequency, linked by a constant, a number that would forever bear his name, Planck's constant. At first, Planck viewed this idea as a mathematical trick, not a revolution. But the universe had other plans. Planck's formula worked perfectly. The blackbody spectrum that had defied all explanation now matched theory to observation with uncanny precision. Though he could not fully grasp its meaning, Planck had unknowingly opened the door to an entirely new world, one that would soon engulf all of physics. 5 years later, a young patent clerk named Albert Einstein would walk through that door. Studying the photoelectric effect, an experiment in which light knocks electrons out of a metal surface, he found that the energy of the ejected electrons depended not on the intensity of light, but on its frequency. Brighter light at the wrong color had no effect, while dim light at the right frequency could free electrons instantly. Classical wave theory could not explain this. The only possible answer was that light itself came in packets, the same quanta Planck had imagined, each carrying energy e⁻². With one stroke, Einstein redefined light as both a wave and a stream of particles, later called photons. His paper of 1905 did more than solve a puzzle, it cracked the foundation of the classical worldview. If light, the purest of waves, could behave like matter, what else might defy the boundaries between energy and substance? This revelation stunned the scientific world. Even Planck himself hesitated to accept it fully. The elegant determinism of Newton's universe, where cause and effect ruled supreme, now faced an unsettling possibility that nature itself might be discontinuous, made not of smooth curves but of sudden leaps. In the following years, the anomalies multiplied. In 1911, Rutherford's discovery of the nucleus created a new puzzle. How could negatively charged electrons orbit around a positive core without radiating energy and collapsing into it? According to Maxwell's equations, any accelerating charge should emit electromagnetic radiation. The atom, by all logic, should destroy itself in a fraction of a second. And yet atoms endured. Something deeper was preventing their collapse, something beyond classical law. It was Niels Bohr who took the next daring leap. In 1913, he proposed a model that blended Rutherford's nuclear atom with Planck's quantum rule. He imagined that electrons could orbit only in specific, quantized paths, each with a fixed energy. They could jump from one orbit to another only by absorbing or emitting a photon, a quantum of light matching the energy difference between orbits. This explained the strange, discrete colors of hydrogen's spectral lines, bright fingerprints of the atom's inner structure. Bohr's model was a revelation. For the first time, theory matched the spectrum of hydrogen with mathematical perfection. But the price of this success was the abandonment of classical logic. Bohr's electrons did not follow Newtonian trajectories. They leapt instantaneously from one orbit to another without passing through the space in between. The continuity of motion, a cornerstone of classical mechanics, was gone. The universe, it seemed, operated through quantum jumps. Still, many physicists resisted the idea. They clung to the dream that quantum effects were temporary, that a deeper classical explanation would one day restore order. But nature continued to defy them. Experiments with atomic spectra, specific heats, and radiation showed again and again that energy existed only in quantized levels. Even Einstein, whose light quanta had begun this revolution, grew uneasy as the implications deepened. He had opened Pandora's box, and the old physics would never be the same. The years after World War I brought new minds to the quantum problem, and with them, a profound shift in perspective. Among them was a young French prince, Louis de Broglie, who dared to ask a forbidden question: if light waves could behave as particles, could particles behave as waves? In 1923, he proposed that every moving particle had a wavelength inversely proportional to its momentum. Matter itself, he suggested, possessed a dual nature, sometimes a wave, sometimes a particle. At first, the idea seemed pure speculation, but 2 years later, experimenters Davison and Germer confirmed it by scattering electrons off a crystal surface. The resulting pattern showed interference fringes, the unmistakable signature of waves. The hypothesis was no longer theory, It was reality. Electrons, once thought to be the indivisible particles of matter, were also waves of probability. The neat boundaries of classical physics had dissolved into ambiguity. This duality demanded a new mathematics, something that could describe particles behaving like waves while still predicting the outcomes of experiments. The answer came from the mind of an Austrian physicist named Erwin Schrödinger. In 1926, he formulated a wave equation that described how the wave function of a particle evolved in space and time. From it, all atomic structure could be derived, energy levels, transitions, and the very shape of the electron's orbitals. But Schrödinger's waves were not waves of matter, they were waves of probability, describing where a particle might be found. And that raised a new and unsettling question: was the electron a real object, or merely a set of possibilities until observed? The classical world had no language for such questions. The universe had become statistical, uncertain, and dependent on observation. Meanwhile, in Germany, a young physicist named Werner Heisenberg was developing his own approach. Working independently, he created a mathematical system, matrix mechanics, that dispensed entirely with visual imagery. His equations described transitions between atomic energy states directly, without pretending to map electron paths. From his formalism emerged one of the most profound ideas in science, the uncertainty principle. It stated that certain pairs of physical properties, like position and momentum, could never be known simultaneously with arbitrary precision. The more precisely you measured one, the less precisely you could know the other. This was not a flaw in measurement, but a property of nature itself. Reality, at its core, was uncertain. The smooth, predictable world of Newton had given way to a restless sea of probabilities. As these discoveries converged, the old order of physics began to fall apart. The comforting determinism that had guided science for centuries was no longer tenable. Atoms were not miniature solar systems, they were clouds of potentialities. Energy did not flow smoothly, it leapt in quanta, and the act of observation itself played a role in shaping what was observed. The quantum world had arrived, mysterious, paradoxical, and utterly transformative, but even as the equations triumphed, many physicists struggled to accept their meaning. Einstein, Bohr, and Schrödinger debated furiously over whether quantum mechanics described reality or merely our knowledge of it. God does not play dice, Einstein protested, unwilling to surrender to the reign of probability. Bohr replied calmly that perhaps it was not for humanity to tell nature how to behave. Their arguments, though philosophical, cut to the heart of science. What is reality, and can it ever be known completely? For the younger generation, however, the results spoke louder than philosophy. Quantum mechanics worked. It explained the stability of atoms, the spectra of elements, and the structure of matter with astonishing precision. Out of its abstract mathematics came predictions that experiments confirmed again and again. The old physics had been overthrown, not by ideology but by evidence. As the 1920s gave way to the 1930s, the new quantum framework became the language of the microcosm. It no longer seemed like a theory among others. It was the theory, the foundation of all modern physics. The universe of certainty had given way to a universe of chance. Every electron, every photon, every atom obeyed the strange rules of quantum mechanics. Reality, it turned out, was not a solid, continuous flow but a mosaic of probabilities. The dawn of quantum physics was not a gentle sunrise but a storm, a brilliant, chaotic upheaval that swept away centuries of assumption. It challenged the very nature of truth, showing that even the smallest entities in nature could defy human logic. It revealed that the universe was not a machine ticking predictably through time, but a symphony of waves and particles, of chance and necessity intertwined. And yet, amid the uncertainty, there was order, an invisible harmony encoded in the equations of Schrödinger and Heisenberg, an elegance that suggested nature's chaos was not random but purposeful in its own mysterious way. The dawn of quantum physics had not destroyed science, it had liberated it. The physicists who stood on that threshold knew they were witnessing the birth of a new worldview, one that would reshape not only physics but philosophy, chemistry, and even technology. From the faint glow of cathode rays to the dazzling precision of quantum mathematics, humanity had crossed into the heart of the atom and discovered that reality was stranger than imagination itself. As the 20th century unfolded, the realm of physics stood on a trembling edge. The old laws that had guided scientists for centuries, those of Newton and classical mechanics, were beginning to crack under the weight of strange new discoveries. It was as though nature itself had been whispering a secret all along, waiting for humanity to listen. And now, in the quiet laboratories of Europe, in the flickering light of discharge tubes and photographic plates, that whisper was turning into a roar. Physicists found themselves in uncharted waters. Experiments no longer behaved in ways that intuition could predict. Light, which had long been understood as a continuous wave, began to act like a particle. Matter, once thought solid and dependable, displayed behaviors that seemed ghostly and uncertain. Something profound was happening in the smallest corners of the universe, and it demanded an entirely new language to describe it. At the heart of this growing storm was a puzzle that refused to be solved: the dual nature of light. In 1905, Albert Einstein, building upon Max Planck's idea of energy quanta, proposed that light itself came in packets, discrete particles called photons. This idea was both brilliant and deeply unsettling. For centuries, experiments like those of Thomas Young had shown that light produced interference patterns, the hallmark of a wave. But Einstein's explanation of the photoelectric effect, where light could knock electrons out of metal surfaces, worked only if light behaved as a stream of particles. The contradiction was undeniable: light was both a wave and a particle, depending on how one looked at it. This revelation shook the foundation of physics. If light could act this way, what about matter itself? Could electrons, protons, and atoms possess such dual behavior? A young French physicist named Louis de Broglie dared to ask that very question. In 1924, he proposed that every particle of matter had a wavelength, a wave like nature tied to its motion. His hypothesis seemed almost mystical at first, but when it was put to the test by experiments like electron diffraction, it was confirmed. Electrons, the very building blocks of matter, could produce interference patterns just like waves of light. The universe was speaking in a new dialect, one written in both particles and waves, energy and uncertainty. This duality upended everything science thought it knew. The atom was no longer a miniature solar system where electrons orbited neatly around a nucleus. Instead, it became a vibrating symphony of probabilities, where energy and matter blended into a strange and delicate dance. The deterministic laws of Newton, which had once seemed eternal, gave way to the probabilistic laws of quantum mechanics. The shift was not just scientific, it was philosophical. The dawn of quantum physics was not a single moment of discovery but a gradual, collective awakening. Across Europe, minds like Niels Bohr, Werner Heisenberg, Erwin Schrödinger, and Max Born were building a new framework, piece by piece. Bohr introduced the revolutionary concept of quantized orbits, where electrons could only exist at specific energy levels, jumping between them by absorbing or emitting quanta of energy. This explained why atoms emitted light at distinct wavelengths. Each jump corresponded to a precise packet of energy. But even Bohr's elegant model soon met its limits. The electron could not be pinned down to a path, nor could its energy transitions be explained in purely mechanical terms. Heisenberg's formulation of matrix mechanics and Schrödinger's wave mechanics, though mathematically different, both sought to describe this elusive realm. And when Schrödinger proposed his famous wave equation, it offered a vision of the electron not as a particle orbiting a nucleus, but as a wave spread through space, a probability field, existing everywhere and nowhere at once. Still, the more the quantum pioneers discovered, the stranger the picture became. The act of observation itself seemed to play a role in determining what was real. When scientists tried to observe an electron, it behaved like a particle. When they didn't, it acted like a wave. This raised a haunting question. Did the electron exist in any definite form when no one was watching? Bohr and Heisenberg argued that nature did not possess definite properties until observed. This idea, known as the Copenhagen interpretation, was as controversial as it was profound. It suggested that reality itself was not fixed but fluid, shaped by the act of measurement. Einstein, deeply uncomfortable with this, famously protested, "God does not play dice with the universe." Yet, time and experiment continued to side with the quantum view. The clash between classical certainty and quantum uncertainty marked one of the greatest intellectual battles in human history. In the classical world, every effect had a clear cause, the universe ran like a predictable machine. But in the quantum world, the future could only be predicted in probabilities, not certainties. This wasn't just a scientific shift, it was an existential one. Humanity had to confront the idea that the universe, at its core, was fundamentally unpredictable. As new experiments tested these theories, the quantum model only grew stronger. The double-slit experiment, repeated countless times with photons, electrons, and even larger particles, confirmed the unsettling truth: particles behaved like waves until observed. Observation didn't merely reveal reality, it seemed to create it. The universe, once thought to be objective and independent, became something deeply intertwined with consciousness and measurement. Yet even amid the strangeness, quantum physics worked. Its equations predicted results with unprecedented accuracy. Quantum theory explained why atoms didn't collapse, why matter was stable, and why light interacted with matter in specific, quantized ways. It laid the foundation for technologies like semiconductors, lasers, and quantum computers. It redefined chemistry, biology, and even cosmology. The challenge to old ideas was not merely theoretical, it reshaped the modern world. But the pioneers themselves remained divided over what their discoveries truly meant. Schrödinger, uneasy with the probabilistic interpretation, devised his now famous thought experiment, the paradox of Schrödinger's cat. In it, a cat sealed in a box with a quantum mechanism was said to be both alive and dead until observed. The idea captured the absurdity and mystery of quantum superposition, an illustration of how bizarre the quantum realm appeared when translated into everyday terms. Heisenberg's uncertainty principle deepened this enigma. It showed that there were limits not just to what we could know, but to what could exist in a definite state. The more precisely we measured one property, like position, the less precisely we could know another, like momentum. This wasn't a limitation of instruments, it was a law of nature. The classical dream of total knowledge was shattered forever. The new physics was not simply an extension of the old, it was a revolution in thought. Quantum mechanics forced scientists to abandon the comfort of visual models and deterministic equations, replacing them with mathematical abstractions and probability functions. The electron was no longer a thing that could be drawn or seen. It became a wave of likelihood, a mathematical ghost describing where it might appear. This shift from what is to what can be required a new kind of imagination. Physicists had to learn to think beyond intuition, beyond the visible world. The quantum domain was a place where common sense failed and paradox reigned, where something could be two things at once, and where cause and effect blurred into one another. As the theory matured, its strange predictions were put to the test again and again, and it never failed. Quantum electrodynamics, developed later by Feynman, Schrödinger, and Tominaga, refined the quantum vision further, describing how light and matter interact with extraordinary precision. Every experiment confirmed that, as bizarre as it seemed, quantum physics was the true language of the universe. By the mid-20th century, the world had accepted the quantum revolution. The atom was no longer a simple structure of orbiting particles. It was a dynamic sea of probabilities, guided by the unseen rules of the quantum world. The discovery did more than change science, it changed how humanity saw itself. We were no longer observers of a fixed reality, but participants in a cosmic play where observation shaped existence. In this dawn of quantum physics, old certainties dissolved into a shimmering haze of possibility. The universe, once a clockwork machine, revealed itself as a living mystery, an ever-evolving web of energy, matter, and consciousness. What began as a challenge to old ideas became a gateway to a deeper truth, that at the smallest scales of existence, reality is not merely discovered, it is created. And so, the dawn of quantum physics was not the end of understanding, but the beginning of wonder. It taught us that the smallest things can reveal the greatest truths, and that the universe, in all its vastness, hides its secrets not in complexity, but in the delicate simplicity of uncertainty. In the strange, invisible world within the atom, humanity found not only a new science, but a new way to imagine reality itself. The strange world of the quantum began to reveal its most fascinating secret through one of its simplest, but most mind-bending discoveries: wave-particle duality. For centuries, scientists believed that light behaved purely as a wave, spreading smoothly through space, producing interference and diffraction patterns that could be measured and predicted. Yet, when experiments like the photoelectric effect and the Compton scattering were studied, they revealed a shocking truth. Light sometimes behaved as if it were made of particles, tiny packets of energy called photons. This dual behavior shattered the old certainty that something must be either a wave or a particle. The universe, it seemed, could be both at once. The mystery deepened when physicists turned their attention to matter itself. In 1924, Louis de Broglie made a daring suggestion that particles of matter, such as electrons, could also behave like waves. He proposed that every moving particle had a wavelength related to its momentum, a delicate wave that guided its motion. His idea sounded almost poetic, but it was confirmed in 1927 when electrons were fired through thin metal foils and produced interference patterns identical to those of light waves. Matter had crossed the boundary into the realm of waves. This discovery redefined what an electron truly was. It was no longer a tiny, solid particle orbiting the nucleus like a miniature planet around the sun. Instead, it became a smear of probability, a wave-like presence that existed everywhere and nowhere until measured. When unobserved, the electron spread out as a wave, capable of interfering with itself, creating patterns of possibility. But when observed, it seemed to collapse instantly into a single point, a particle detected at one spot. The act of measurement appeared to decide the electron's fate, transforming potential into reality. This idea reached its most haunting expression in the famous double-slit experiment. When electrons were sent through two narrow slits one at a time, they still produced an interference pattern, as though each electron had passed through both slits simultaneously as a wave. Yet, when scientists tried to detect which slit an electron actually passed through, the pattern vanished. The electron behaved like a particle instead. Observation changed the outcome. The experiment became one of the most powerful demonstrations of the dual nature of matter, showing that the quantum world did not follow the logic of everyday experience. Wave-particle duality forced scientists to rethink what it meant to exist. In the quantum realm, entities like electrons do not have definite locations or paths until observed. Their existence is described by Schrödinger's wave equation, which calculates probabilities rather than certainties. The electron, then, is not an object traveling through space, but a cloud of potential outcomes. A living equation awaiting interaction. This realization made the boundaries between energy, matter, and observation blur into one another. The impact of this duality stretched far beyond theory. It became the foundation for modern quantum mechanics, influencing how atoms, molecules, and even light are understood. It explained why electrons occupy certain energy levels in atoms and why chemical bonds form as they do. It opened the door to technologies like electron microscopes, which exploit the wave-like behavior of electrons to see structures smaller than light can reveal. Later, it would lead to quantum computing, lasers, and countless devices that define the modern world. Wave-particle duality also raised deep philosophical questions. If the act of observation changes reality, then what does it mean for something to exist independently of being seen? The line between the observer and the observed began to fade, suggesting that consciousness itself might play a role in shaping the physical world. Though this idea remains debated, it captures the wonder and strangeness that duality introduced. In the end, the discovery that electrons and photons could be both waves and particles revealed the hidden poetry of nature. That reality is not a rigid structure, but a symphony of possibilities. Wave-particle duality became a symbol of the quantum revolution, a reminder that beneath the ordinary lies a world of paradox and beauty, where the smallest things in the universe dance between being and becoming. In the unfolding story of quantum physics, one revelation stood above all in its power to unsettle the human mind: the uncertainty principle. It was born not from a laboratory accident or a dramatic discovery, but from a deep and painful realization by Werner Heisenberg in 1927. As scientists tried to describe the behavior of electrons within the atom, they found themselves confronted by a strange truth. No matter how precise their instruments became, there existed a natural boundary beyond which knowledge itself could not go. The more precisely one tried to measure the position of an electron, the less precisely one could know its momentum, and vice versa. It was not a flaw of technology, but a fundamental feature of reality, nature's own rule of secrecy. This principle struck at the very heart of classical physics. In Newton's world, every motion could be predicted, every event explained through cause and effect. If one knew all the forces and positions of particles, one could, in theory, predict the future of the universe. But Heisenberg's principle destroyed that dream. The universe, at its deepest level, was no longer a place of perfect order, but a landscape of probabilities and limitations. The electron could no longer be pinned down like a marble rolling on a table. It was a cloud of uncertainty, existing everywhere and nowhere until observed. Heisenberg realized that the act of observation itself disturbed the object being observed. To see an electron, one must use light, but the photon used to illuminate it inevitably alters its motion. In trying to look, one changes what is being looked at. Thus, the universe does not yield its secrets without consequence. This idea was both scientifically profound and philosophically haunting. It suggested that knowledge of nature always came at a price, that the more we tried to see, the more we changed what we sought to understand. For many, this was difficult to accept. Albert Einstein, who had helped shape the quantum revolution, could not reconcile himself with this limitation. He believed that uncertainty was a sign of an incomplete theory, famously insisting, "God does not play dice with the universe." Yet experiment after experiment confirmed Heisenberg's insight. The uncertainty principle was not a product of ignorance, but a built-in truth about existence. Nature, it seemed, operated through probabilities rather than certainties. This realization transformed the way scientists viewed the electron and the atom. The electron was not moving along a clear, predictable orbit but existed in regions of probability, described by Schrödinger's wave equation. Each region represented the likelihood of finding the electron in a given space. This was the birth of the quantum cloud model of the atom, a dynamic, uncertain, and elegant vision of subatomic reality. The uncertainty principle also changed how scientists thought about measurement and reality itself. It revealed that observation was not a passive act of watching, but an interaction that influenced the outcome. The observer and the observed were intertwined in a delicate quantum relationship. The world was no longer an objective stage where events simply unfolded. It was a participatory theater where observation shaped what could be known. This new understanding went beyond physics. It touched philosophy, psychology, and even art. It redefined human perception of truth and knowledge. The certainty of the classical world gave way to a universe of ambiguity and possibility. It forced humanity to embrace the idea that not everything could be known, that mystery was not a failure of science, but a fundamental part of existence. The uncertainty principle became the guiding compass of quantum mechanics, the invisible rule that shaped everything from atomic behavior to the vast processes of the cosmos. It explained why atoms do not collapse, why particles cannot occupy the same state, and why energy fluctuates even in empty space. It revealed a universe that was alive with movement and probability, never static, never still. Heisenberg's principle, though born in mathematics, spoke deeply to the human experience. It reminded us that the quest for knowledge is endless, that every discovery opens a doorway to deeper questions. In uncertainty, science found not despair but wonder, a recognition that reality is richer than the human mind can fully grasp. In the quiet world inside the atom, where electrons flicker between being and non-being, uncertainty reigns not as a flaw, but as a law of creation. It is what gives the universe its texture, its motion, its life. The uncertainty principle stands as one of the greatest truths ever uncovered, that even in the smallest spaces, the cosmos guards its mysteries with elegance, allowing us only glimpses of its infinite dance. As the dawn of quantum physics illuminated the unseen world within the atom, humanity faced the task of rebuilding its understanding of matter from the ground up. The old picture of electrons circling a nucleus, like planets around the sun, had fallen apart, replaced by something stranger and more elegant. Out of this new age of discovery arose the quantum model of the atom, a vision that would forever change the way scientists viewed the structure of reality itself. It was no longer a simple mechanical system governed by predictable motion, but a dynamic realm ruled by probability, energy, and uncertainty. The birth of this new atomic model began with the insights of Niels Bohr. In 1913, Bohr proposed that electrons could only occupy certain specific energy levels around the nucleus. They did not spiral inward or outward freely. Instead, they leapt between these levels by absorbing or releasing distinct packets of energy, known as quanta. This model explained the mysterious patterns of light emitted by hydrogen atoms, each line representing a jump between energy states. Bohr's atom was revolutionary, yet it still relied on a partly classical picture, with electrons tracing circular orbits. It was a step into the quantum world, but not yet a full embrace of it. As more experiments revealed the true behavior of electrons, the need for a deeper theory became undeniable. Erwin Schrödinger took the next leap by describing electrons not as particles in motion, but as waves of probability. His wave equation, elegant and precise, replaced orbits with orbitals, regions where an electron was most likely to be found. The atom, once imagined as a miniature solar system, now became a cloud of possibilities, a shimmering haze of energy where boundaries blurred and certainty disappeared. This was not a failure of understanding, but an evolution of it, a realization that nature itself did not operate in straight lines or perfect circles, but in patterns of probability and resonance. Werner Heisenberg added another layer of truth with his uncertainty principle. He showed that it was impossible to know both the exact position and momentum of an electron at the same time. The more precisely one tried to measure one property, the less certain the other became. This principle wasn't a limitation of tools or observation, it was a natural law. It meant that the electron's position wasn't fixed, it existed in a state of potential, only becoming definite when observed. The atom was not a solid structure, but a dynamic, living field of possibility. Together, these ideas formed the foundation of quantum mechanics and gave birth to a new understanding of atomic structure. Electrons were not objects orbiting like planets, but standing waves confined by the nucleus's pull. Each electron had its own energy state, described by quantum numbers, and the arrangement of these states determined the behavior of elements and the richness of the periodic table. Quantum mechanics explained why matter was stable, why atoms formed bonds, and why the world around us existed as it does. The quantum model also revealed that the atom was not isolated. Every atom interacted through the exchange of energy and particles, bound together by the fundamental forces of nature. Quantum field theory expanded this vision further, describing particles not as independent entities but as excitations of underlying fields that filled all of space. The electron, then, was not a tiny sphere but a vibration, a ripple in an invisible ocean of energy. This new atomic picture transformed science and technology alike. It laid the groundwork for the invention of semiconductors, lasers, and quantum computers, tools that now power modern civilization. It explained why chemical reactions occur, why light behaves as it does, and even why the stars shine. What began as a quest to understand the atom became a key to unlocking the universe. Yet beyond its scientific triumphs, the quantum model of the atom carried profound philosophical meaning. It taught humanity that reality is not fixed or mechanical, but fluid and probabilistic. The atom, once thought to be the solid foundation of matter, turned out to be mostly empty space, governed by invisible rules of chance and interaction. This realization reshaped how we view existence itself. Certainty gave way to possibility, and the rigid clockwork universe of Newton yielded to a cosmic dance of energy and probability. In this vision, the atom became a microcosm of the universe, a place where creation, destruction, and transformation coexisted in harmony. It showed that the same laws guiding the smallest particles also shaped the grandest galaxies. Everything, from the glow of a candle flame to the fusion of stars, arose from the same quantum principles. The shaping of the quantum atom was not just a scientific achievement, it was a philosophical awakening. It revealed that beneath all matter lies mystery, a structure that is both precise and unpredictable, measurable yet infinite in its depth. Through quantum mechanics, the electron was reimagined not as a simple charge, but as a symbol of nature's dual nature. Order within chaos, certainty within uncertainty. The quantum model of the atom stands today as one of humanity's greatest achievements, a bridge between the known and the unknowable. It taught us that the universe, at its core, is not made of things, but of possibilities, and that within every atom lies the silent hum of creation, a reminder that existence itself is built from the poetry of the invisible. When the curtain was finally lifted on the quantum world, humanity realized that it was not merely learning about atoms, it was redefining the very nature of reality. The final legacy of quantum physics was not just in discovering how the electron behaves or how atoms form matter. It was in transforming our understanding of what it means to exist. The smallest particles in the universe had revealed truths that stretched far beyond science, touching philosophy, technology, and even the boundaries of imagination. Quantum physics did not simply describe the world, it changed how we think about it. Before quantum theory, the universe was seen as a grand machine, governed by absolute laws. Every effect had a cause, every motion a reason. The atoms of matter followed predictable paths, and in theory, if one knew the position and velocity of every particle, one could predict the entire future. This was the comforting vision of classical physics, certain, orderly, and logical. But when quantum theory emerged, that certainty crumbled. Reality, once thought solid, dissolved into probabilities. The universe was no longer a clockwork device, but a living field of possibilities. Quantum physics redefined matter at its most fundamental level. The electron was no longer a tiny ball orbiting the nucleus, it became a wave of potential, a cloud of energy existing in many states at once until measured. Every act of observation transformed what was possible into what was real. This idea, that the observer plays a role in shaping reality, was one of the most profound shifts in human thought. The boundary between the observer and the observed faded. The universe was not an indifferent machine, but an interactive, participatory system, where consciousness itself seemed to have a role in creation. Through this understanding, the electron became a symbol of duality. Both wave and particle, both energy and matter. It existed in superpositions, capable of being in multiple places or states at once until observed. This strange behavior was not an illusion, but a fundamental truth of nature. It showed that reality, at its core, is not fixed but flexible, not certain but statistical. The universe became a place not of strict laws, but of probabilities that unfold according to patterns of quantum behavior. This revelation redefined technology and the human relationship with the physical world. The principles of quantum mechanics led to inventions that reshaped civilization: transistors, lasers, nuclear energy, quantum computers, and communication systems that rely on entanglement and superposition. The same rules that governed electrons inside atoms now powered global communication and computation. Humanity had harnessed the strange logic of the quantum world to build a new age of technology. But the impact of quantum theory went beyond machines and inventions. It reshaped thought itself. It forced philosophers and scientists alike to confront questions that had once belonged only to metaphysics. If observation affects reality, then what does it mean to know something? If particles can exist in multiple states at once, what does it mean for something to be? These were no longer poetic questions but scientific ones. The boundaries between physics and philosophy blurred as quantum theory pushed the limits of what could be understood. The quantum revolution also changed how humanity viewed matter and energy. According to Einstein's famous equation, E=mc², energy and mass were two sides of the same coin. Quantum mechanics extended this idea, showing that the universe is woven from fields of energy that fluctuate even in empty space. What appears as nothingness is, in fact, alive with virtual particles flickering in and out of existence. The universe, even in its silence, hums with creation. This redefinition of matter and reality revealed that everything, from the smallest atom to the largest galaxy, is interconnected. Quantum entanglement showed that particles can remain mysteriously linked across vast distances, their states correlated in ways that defy classical explanation. It hinted at a universe where separation is an illusion and where all things share a deep, hidden unity. Through quantum physics, humanity learned humility. The dream of absolute knowledge faded, replaced by the beauty of mystery. The electron, once a simple particle, became a gateway to understanding that reality is not a single story, but a tapestry of countless possibilities. Each experiment revealed not just how the universe behaves, but how deeply intertwined we are with it. The redefinition of the electron, and of matter itself, became one of the greatest intellectual achievements in history. It taught that what we see is only a shadow of what truly exists, that beneath every solid surface lies a world of vibrating energy, uncertainty, and endless transformation. The quantum world is not chaos, it is an elegant complexity, a dance between chance and law, order and mystery. In the end, quantum physics gave humanity more than equations or theories. It gave perspective. It reminded us that certainty is an illusion, that knowledge has boundaries, and that within those boundaries lies wonder. It showed that even in the smallest spaces, the universe contains infinite depth. Inside every atom, within every electron, is a reflection of the cosmos itself, a reminder that the universe is not merely observed, but also lived. Quantum physics redefined not only the electron, but the spirit of exploration itself. It proved that the search for truth is not about conquering mystery, but embracing it, not about control, but about understanding. In the realm where particles flicker between existence and possibility, humanity discovered its greatest revelation, that the universe is not a machine, but a miracle, and that inside the atom lies the story of everything.